delighted to be here to represent climate community, monsoon community, to talk about monsoon's past and present future. I should thank all of you that you have given me an opportunity to talk to you in this important meeting. And so I'll spend about 45 minutes talking about monsoons. And I'll start with how was past monsoon and what is present and what we can expect in future warming climate. I should confess it that I am not an expert in paleoclimate or paleo monsoons. I have not done any research on that, but I will spend a few minutes talking about, just to have a continuity of my presentation. I will start with the past climate, but I will spend more time on present and future monsoon. So this is the outline of my presentation. I will talk about paleo records and some results from paleo modeling, paleo monsoon modeling. And then I will talk about basic theories of monsoon, how we define monsoons, etc. Then what we observed about present monsoon in terms of using observed data and also models in terms of variability, teleconnections, monsoon extremes, etc. Then finally, I will talk about what we can expect in future warming climate, because global warming is happening. So what we should expect for monsoon future climate. So I will talk about future climate change projections from IPCC models. So as all of us, of course, you are all more familiar with the past monsoon climate. In the past, of course, monsoon varied at a geological time scale based on so-called continental drift, the changes in the solar insolation, the so-called Milankovitch cycle, organic forcing, and carbon dioxide concentration in the atmosphere. All of you know that the Indian plate collided with the so-called Eurasian plate about 55 to 45 million years ago. As a result, the Tibetan Plateau and the Himalayan mountains were developed. And then the Tibetan Plateau has reached its modern height, and the East Asian monsoon established after 23 million years. So the South Asian monsoon came first, the East Asian monsoon was developed much later. However, the Himalayan mountain range south of Tibetan Plateau became taller than the average height of the Tibetan Plateau around 15 million years. Same time, Iranian Plateau also was experiencing an uplift. That is very important phenomenon if we talk about monsoon dynamics. Iranian Plateau plays an important role. Increase of the height of the Himalayas and also the Iranian Plateau uplift were concurrent with the strengthening of South Asian monsoon. Since then, of course, all of us know that South Asian monsoon in general and Indian monsoon in particular had experienced fluctuation at different time scale, which I will describe in detail. This is the famous paper by Molnar's review in geophysics, the famous geologist on continental drift, how the monsoon has come, what is the role of Tibetan Plateau, etc. This is the continental drift which is shown. So at that 50 million years ago, approximately, when India collided with Eurasia, that was the beginning of Himalayas as well as the monsoon phenomenon. And this is the modeling results from a famous paper by Liu et al. On scientific reports. So this is, they used a coupled model, but then using the paleo data, and they tried to simulate how the monsoon was the earlier years. Starting from top left, it is some 60 million years ago. As you see that India still not was with India still is Indian continent was still drifting. So we did not have a monsoon. The green colors are northern hemispheric monsoon, and yellow and oranges are southern hemispheric monsoon. And you can see that still India is away from Eurasian subcontinent. And around 40 million years ago, it was very close to Eurasian continent. It was colliding with in Eurasian continent. So monsoon process has really started. So then the middle one, left-hand side is around 25 million years, and right-hand side is 10 million years, and lowest bottom and left-hand side is the present monsoon. And you can see that for the South Asian monsoon was developed, South Asian monsoon was much earlier than the East Asian monsoon. You can see East Asian monsoon was very much visible only around 10 million years ago. And after the Tibetan Plateau is completely developed, and also the Iranian Plateau. And the present monsoon, you can see that it's African monsoon. So the development of monsoon, African monsoon was there even 60 million years ago. So and it is probably one of the oldest monsoon phenomena. And also you have yes, in the Asian region you have South Asian monsoon as well as East Asian monsoon region. Now we talk about the coupling or co-process between these two monsoons, but the origin was different. And this is the same paper, but it shows how the top level is about 850 millibar rainfall during June to September. Yeah, you can you can easily see that 60 million years ago the cross-continental flow was there, but it was fully developed and made a monsoon flow around. I think so much prompt is coming up. Okay, so around 40 million years ago, the so-called southwesterly winds have started coming. But just you can see the East Asia, there was not much monsoon. So all this was going from land to sea, the winds. It started in Southeast Asia, and you can see the red lines. This is how the Tibetan plateau was developed. And you can see around between 10 and 15 million years ago, the East Asian monsoon. You can see the winds are from south westerly winds are turning into easterly winds there. So that is the so-called East Asian monsoon develop, and the present monsoon is the last extreme, right? And so this is again a summary of what DO has told. The last bullet I will read. The monsoons of East Asia and North Australia did not appear until the Miocene, and the establishment of simulated low-latitude South Asian, North Australian monsoon appeared to have strongly depended on the location of mainland India or Australia or Australian monsoon associated with the northward plate motion without much relation to the plateau uplift. On the contrary, the establishment of middle-latitude East Asian monsoon was mainly controlled by the uplift of Tibetan plateau. So it has an important role to play. So these are all model results, so there could be some uncertainties in terms of physics involved in this. And as all of us know, this is the so-called Milankovitch cycle. This is about 100K, 40K, and 26,000 years of cycle of different process of the Sun-Earth relationship in terms of eccentricity, obliquity, and also the precision. And this kind of variability also you can expect from monsoon. So this is a famous paper by Kathiat et al. By 2016 when scientific reports. So it shows how the monsoon varied with respect to solar cycle. And so both Asian and South Asian monsoon subsystems exhibit coupled response that's very important to changes in the northern hemispheric summer insolation without significant temporal lags, supporting the view that tropical and subtropical monsoon variability is driven directly by precision-induced changes in the solar insolation, the top of the atmosphere. And comparison of the North Indian record with both Antarctic ice core and the sea surface temperature records from the southern Indian Ocean over the last glacial period do not suggest a dominant role of southern hemisphere climate process in regulating the monsoon variability on millennial to orbital timescales. That's very important aspect which this paper has brought out. And this is again same authors but different papers, which says that there's a beautiful temporal relationship between the large scale hydroclimate changes which was happening at that time and the intervals marking the significant socio-political developments like Indus Valley, Vedic civilization, Harappan civilization, and also the different kingdoms over that region. So they used speleothem from Sahia. There's a cave called Sahia. So you can use this shown in the India map. You can see it's extreme north. So they used that map and they have shown this how the monsoon variability was changing and how the civilization was happening in between, and also how the different kingdoms prospered and how the kingdom have completely disappeared in with respect to time. So all it has important the monsoon variability, climate variability has an important role to play in terms of Indian civilization. It's very important to note. Good. So, and with the recent years, there's a tree ring record observations from this paper from Bodgaonkar. He was a scientist at IIT Pune. 523 years of data from 1481 to 2003. So they have used three sites, forest sites in Kerala and southern state, and they use this. And this is the data from 1418 to 2003. And the last few years where the observations, re-engaged observations are there as projected the second and third row. You can see that how the variability is there. So there's large scale variability. And when I talk about little later, so it's also the red line shows the smoothing time series of monsoon rainfall. And you can easily see that it's a large scale multi-decadal variation. So which I will talk about the multi-decadal variation a little later, why it is important, how to predict, etc. And so there's a large scale internal variation as well as large scale multi-decadal variation. So this is the observations from again tree rings. These are all again proxies, but as we know that the solar insolation changes which occurred with respect to the solar cycle, the so-called the orbital changes, etc. It's really affected monsoon rainfall, monsoon climate system. But even if you assume that in a particular period the solar insolation is same, still we can have different response to the by monsoon depending upon the internal feedbacks, internal dynamics of the monsoon system. So this is a very famous paper published in Nature Communication by IAC group at Bangalore. So they say that this an insolation, and you can see that the two branches are going. One is the dominant during the deglacial period. It's about 22 to 10 Ka, and the second one is the recent 10 Ka to the present one is where the dominant is during the Holocene, and there are two processes which are happening in as far as the monsoon feedback. One is so-called the energy available from the system, especially from the outer space, and which is given to the climate system, monsoon climate system, and also there is so-called the instability, so-called the instability of the atmosphere. So both can play an important role, which I shown it here. You can see that you can put a simple equation of P is precipitation minus evaporation in terms of the Q dive. It's nothing but the total energy available, energy input available, and TGMS is nothing but total gross moist stability. And you can see that the recent years, basically the Q dive was more important than compared to the total gross moist stability. But in the initial years, in the later years, the previous years, 22 K to 10 K, for example, that was the rise of water vapor. The importance of thermodynamics was very important because there was a role of increase in sea surface temperature during that period. So, but during the recent periods, cloud feedback effects were found very important. And very important thing is all during the whole period, the solar cycle, solar insolation was same. But internal dynamics can play important role in spite of constant solar insolation in terms of climate feedback. So within the monsoon system, the monsoon rainfall can be different. So this is a very important study, which is brought down by its people. So if you really want to understand monsoon and different time scale, if it is 100K, then it is basically the solar radiative forcing is very important, and that can explain the whole cycle of 100K. And when you talk about 10K, 10,000 years, then solar cycle as well as the water vapor, which was shown by this paper, is very important. And recent years, if you take last 100 years or 1,000 years or so, it is solar cycle, water vapor, and also the moist stability and instability is also plays important role. When you talk about the present day climate, the present day monsoon variability, and solar radiation, water vapor, moist stability, as well as circulation plays important role. Okay, so these are all dominant forcing and determining the variability of monsoon at various time scale from interannual to 100 millennium. And this is the present day climate with us. So our rainfall observations, especially from India, dates back almost 200 years now. So first observation I remember is 1850 or so, 1840 or so, I think 1840. And so we have the rain gauge observation for 150, 170 or 200 years. And so we can really understand how the monsoon varied with using the rain gauge data. So India is we are all, as Indians, we are all fortunate that we have two monsoons, good monsoon, southwest monsoon from June to September, and we have a northeast monsoon. So northeast monsoon already has been set in by this year, October to December. So that is predominantly is the dominant in the southern peninsula, mostly Tamil Nadu, Andhra, Kerala, the region. But whereas 70 to 90% of monsoon rain, annual rainfall comes from southwest monsoon, which is very important aspect. So our whole energy is spent on understanding what do you mean by southwest monsoon, how the monsoon varies from different time scales, whether can we predict it, what are the issues in terms of predictions. Now with the climate change and so-called global warming, now the question is whether we'll have same monsoon, whether we can have different monsoon, what are the different characteristics of monsoon we can expect in future climate. So some salient aspects I will discuss in between. So I will talk about the basic concept of monsoon. I will not go in detail because I don't have much time, because I can almost talk about 1 hour about the theories of monsoon. But basically the so-called land sea temperature contrast is the basic driving force of monsoon. And even when you explain the paleo monsoon, we always talk about the so-called relationship, solar cycle, solar insolation, the type of atmosphere, temperature relationship, etc. All described, all discussed in terms of so-called land sea temperature contrast. And if you see the left-hand side, that is the temperature. It's a sea level pressure. So temperature and pressure are related. More temperature is less pressure. More cold temperatures mean more pressure. So this left-hand side is the sea level pressure distribution, which shows that pressure is high at northern latitudes, and over Indian Ocean the pressures are low. So the pressure gradient is from north to south, and basically from higher pressure to lower pressure. Whereas when our summer season comes June to September, the whole pressure gradient gets reversed. You can see that southern Indian Ocean is having more pressure. So and Indian mainland is having low pressure. That means mainly because of the high temperature. So it is again driven by solar insolation. Heating of the land surface, so we get higher temperature, so low pressure. So that's a pressure gradient. So the pressure gradient reverses mainly because the temperature gradient reverses. So this is once the pressure gradient reverses, the flow of air will from high pressure to low pressure. So air will come from southern hemisphere, turn it into Indian Ocean, so South Indian Ocean, North Indian Ocean, and turn it into Indian region. So that's the basic philosophy of monsoon, which was discussed many years ago. But now the recent theories, recent observations all clearly suggest that land sea temperature contrast is not a good explanation how you describe monsoon, especially South Asian monsoon. And this is the again same pictorial representation of two different seasons, one in January and July. And January you can see that all winds are all northeasterly winds, and in the July you get winds mostly of southwesterly wind over the North Indian Ocean. And so there's an outflow from southern hemisphere. It goes up and rotate, and it crosses the equator and comes as a southwesterly winds over the Indian region. So these are the basic, and this shading is basically sea surface temperature, how the ocean is warm. And you can see January, the whole equatorial Indian Ocean is very warm with temperatures about more than 29 degrees. But during monsoon season, the equatorial warm water will remain same, but there is always a northward movement of warm water, especially over Bay of Bengal as well as over the West Pacific. You can see water is ocean become much more warmer than January, and the warm water over the Bay of Bengal is very important in terms of genesis of low pressure system, weather systems, and which ultimately cause more rainfall over Indian mainland. Okay, and this is the beautiful flow of 850 millibars at 1.5 kilometer, how the winds flow from southern hemisphere, crosses the equator and moves. So we have a blue shading is given there. The winds are very strong, and so we have so-called low-level jet. That means it's maximum north should be reducing, winds should reduce, and south also wind should reduce. So this is a jet stream, so-called low-level jet stream, and it's mainly caused by the classical flow. So this is the theory of monsoon. In summary, the first theory came from UK scientist called Halley, and he hypothesized that main cause of the annual cycle of monsoon circulation was the differential heating between ocean and land caused by the seasonal march of the sun. And Halley said that how you can then, if it is only simple pressure gradient, then you should expect winds from high pressure to low pressure. The wind should be exactly southerly winds. but we are getting southwesterly winds. But then that he explained in terms of so-called S-rotating, so-called we call Coriolis force, because the Coriolis force in the northern hemisphere winds will flow to the right. So we have southwesterly winds, so that can be explained. So you have a terminal temperature gradient, so winds will come from south high pressure to low pressure, but then when it crosses the equator, it turns towards right, and we have southwesterly wind. And Webster later added the moist process, the heating, latent heating of the atmosphere is very important to drive the monsoon. So we all thought that monsoon is typically a big, gigantic sea breeze. Sea breeze, you must have noticed it, especially people staying in the east coast of India will notice this in daytime. What happens? Daytime, the warm temperature over day, the day gets heated much faster than ocean. So then there is a warm air going up and coming down as a cold sea breeze from the ocean. So temperature will. So that's why all coastal stations, the temperature are a little moderate because it's all controlled by cold sea breeze in the daytime. And so the same kind of analogy was used to explain monsoon in terms of large scale monsoon circulation. But the problem in the low, so-called the land sea breeze was, if you really assume the land sea temperature contrast is the main cause for monsoon, it cannot explain. Only one quick loophole in this, that in the modeling framework, if you remove all this land, assume that it's, everything everywhere is ocean, but you put the solar energy and the solar radiation going up and all the during summer, and so the temperature contrast, everything you put it, then you get a monsoon. So-called we call aqua planet, where the planet is full of ocean water. So then still you get a monsoon, but monsoon is not that severe monsoon what we are experiencing, but still you can get a monsoon. But that's in models. And another important aspect which is very, very concerned is that if you assume that land sea temperature contrast is very important, so if it is more in a monsoon season, then we should expect more rainfall. So, but if you really plot, I did not show the plot, if you really plot a graph, scatter plot between the temperature contrast between land and ocean and monsoon rainfall, the relationship is negative. Very, very surprising. So that means more monsoon means less temperature gradient, and less rain or more temperature. It's just the reverse of what we are thinking of. So the land sea temperature is still very important, but it cannot really explain the monsoon variability in terms of, especially in terms of seasonal yearly cycle seasonal variations. So land sea temperature theory is not being discussed nowadays by many people, but some people still use it in research papers to explain some phenomena which we are experiencing. So basic theory now says it is nothing but it's a northward propagation of so-called intertropical convergence. So monsoon is nothing but the northward propagation. So here the map is showing the blue is everything in the southern hemisphere, austral summer, and what is the boreal summer is shown as red. And there the evaporation is much more, so precipitation is much more than evaporation. And you can see how the things are changing. You see the southern over the Asian monsoon region, there's a huge northward propagation of this ITC set happening. And that is nothing but the monsoon. And this is not happening everywhere. You can see that it's happening in Africa, it happens in Australia, to some extent it happens in North America, but everywhere not. For some Eastern Pacific, it doesn't happen that kind of northward propagation. So monsoon can really defend in terms of the specific geographical northward propagation of ITC set, and how the variability can be explained in terms of its position as well as its the strength of the ITC set. So any activities within the ITC set can be explained to explain the variability of monsoon. So this is the theory which shows. So if you really go with that kind of aspect, then this is the global monsoons which we have. We have South Asian monsoon. This is a typical condition which we have put. That means the local summer minus winter precipitation should exceed 2.5 millimeter per day, and local summer precipitation should exceed 55% of the annual total. So then if you will get this kind of monsoon. We have Australian monsoon, South Asian, East Asia, North African, South African, South American monsoon, North American. Out of all these monsoons, South Asian monsoon is the most important, and South Asian monsoon is very, very strong in terms of its global energetics and how the teleconnections are connected with Asian monsoon. So South Asian monsoon plays an important role not only over the region but the whole globe. And it also has an impact on the El Niños and La Niñas and all. So South Asian, and also South Asian monsoon is less predictable than any other monsoon. Their complexity is much more. So we are in a really a big. We are handling a very, very serious issue of serious but beautiful problem of South Asians. I should say that it's a beautiful problem. It's a very challenging problem, but it's a very beautiful. This is the monsoon rainfall. Looks like this is west coast. You have maxima, northeast you have maxima, another maxima. So it's East Central Asia, East Central India, and Pakistan gets very less rainfall, like Western Rajasthan. And this is the right hand side shows the variability. Variability is in northwest India as well as Rajasthan, Gujarat, as well as Pakistan is much more, and northeast India gets very less variability. And in the monsoon season, all the 122 days it doesn't rain. It rains only a few days. That's called rainy day. IMD defines 2.5 millimeter or more. So this is the left hand side shows the rainy days. It typically goes with the monsoon seasonal rainfall. Right hand shows the rainfall, which is more than 65 millimeter per day. So that is to be IMD calls heavy rainfall, heavy rainy days. And you can see that it's all again related to Central India, Northeast India, and West Coast. And this is a very interesting diagram which I thought I will share with you. Is that as I told that out of 122 days, all the days it doesn't rain. So it rains in only few hours. The question is, even in few hours, a few days, it doesn't rain all 24 hours. Now, the question is, how many hours it rains? So this is a basic question which we need to answer. And so we have done some analysis using IMD self-recording rain gauges, they mean automatic rain gauges, and we try to calculate it. So you can see the left-hand side is total rain hours in monsoon season. Out of 122 days into 24 hours, we have this one in very few, especially West Coast where the numbers are 200, 300. And this is the right-hand side shows the number of hours required to get that 50% of the seasonal total. Again, it comes down. I'll give you a good example. In Ahmedabad, when I was working in the initial years of IMD, it was annual rainfall is about 80 centimeter. Out of 122 into 24 hours, it rains in Ahmedabad only 120 hours, just 120 hours. And half of the rainfall comes in 16 hours. So you can think of what is the characteristic of monsoon rainfall. First few spells, it comes as very, very heavy rains, and remaining all 1 millimeter, 2 millimeter. So it has implication in terms of water resources management. First rain comes in heavy rains, it simply flows off, run off, and remaining comes in a small spell, 2 millimeter, 3 millimeter. Before it reaches the surface, it evaporates. So unless you have a very foolproof kind of a dedicated water management systems, will ultimately at the end of monsoon season, we say that there is no rain, there is no water. So that's so it's very important to see. And recent analysis which we have published, paper is coming out in a research paper. I'll just show you the left-hand side, top left-hand side. Over Central India, the first red curve shows how the cumulative rainfall amount and cumulative rain hours is going. Now, for 50% rainfall, you don't need, earlier days is to get 30 hours to get the 50% rainfall. Now you need only 25 hours or 24 to 25 hours. That means the number of hours required for getting the 50% rainfall is reducing. So that means it comes in very, very heavy spells nowadays. It's a very important aspect. And this is and monsoon, as I told, monsoon varies in different time scale, diurnal, the seasonal, the synoptic time scale, then the intra-seasonal, in the so-called 15 to 30 days time scale, then intra-annual, then so-called multi-decadal. So this is the diurnal variation, which left-hand side shows the amplitude of the diurnal cycle. Right-hand shows the maximum. As I told that every day it doesn't rain every hours, but in some regions there are specific time in which it rains more. It's not that it doesn't rain all the hours. It may rain every time, but it rains more in specific hours. And over Central India as well as the northern parts of India, it is in the afternoon. So basically the afternoon heating that causes the kind of convective activity and rains more. But what I will highlight is the close to foothills of Himalayas in the early morning. So there the rainfall comes in the early morning hours, mainly because there's a katabatic wind which comes from the the Himalayas, and we have a so-called monsoon flow, and it converges together. You get early morning beautiful rain. Okay, and this is how the rainfall for the different hours. You can see how between 12 UTs and 15 UTs, how the rainfall over Central India is picking up, and the early morning how the rainfall is picking up in Himalayas. So beautiful. And if you really do take a daily rainfall and do a spectral analysis of different parameters done by B.N. Goswami, and you can see the left-hand side top is the frequency, spectral analysis of wind rainfall, and right-hand side is 850 millibar wind anomalies. You can see that there are a lot of peaks. One is in the smaller time scales of 3 to 5 days, and then the intra-seasonal time scale, one is in 10 to 20 days time scale, another is 30 to 60 days time scale. The 3 to 5 days is basically, it's called synoptic scale. It's all caused by monsoon weather systems. When it comes to the lifetime is about 3 to 5 days. So that is causing rains, a lot of rains. And then we have a beautiful intra-seasonal time scale of, one is the lower time scale, 10 to high frequency, 10 to 20 days, and 30 to 60 days another. And 30 to 60 days is closely related to the so-called Mandarin-Julian oscillation, or MJO, which is basically a global phenomenon. And this is a weather system which are caused during, which are formed during monsoon season and causes a lot of rainfall June, July, August, September. And this is how the rainfall contribution by each system. And you can see that along the path of the monsoon, the weather system, it causes a lot of rain. And this is a beautiful, we call home diagram of basically nothing but you take a longitude and plot the time versus the latitude. You will see how the northward propagation is happening. And this first is 90 degree east, and the bottom one is 80 degree. You can see the beautiful northward propagation of this is all convection. Anomalies. So within the broad range of 10 to 90 day periods, there are two periods are dominant. One is 10 to 20 day cycle, and this 30 to 60 day cycle. The question is, we understand now. I will not go in detail, but I would like to highlight that we understand this physical mechanism mostly, and still there are unknowns as there are gray areas. And also we are able to predict this kind of intra-seasonal variability with moderate accuracy. So we should be happy. So the understanding of intra-seasonal variability and its prediction is very important. And it is associated with the intra-seasonal cycle. We have a phenomenon called active break monsoon. Active break cycles in the phases in the monsoon, and there is a definition proposed by us in using monsoon board region data. And this is the one particular season. All red bars are shown as a break, and all green are active phases. So you can see that in monsoon season there are typical break phases and also typical active phases. And how the OLR is nothing but as a proxy for convection. The break spell or red means above OLR means less convection. And you can see in the break spell you get less convection over Indian monsoon, but the East Indian Ocean you can see blue, there's all above convection. And also in the Western Hemisphere, the West Pacific, Northern West Pacific is active in convection and less suppressed in the active spell, it just gets reversed. So it's a beautiful active break cycle. The question is, can we predict? Because it's very important for the farmer. The farmer's time period is almost 10 to 15 days for his preparations for doing anything. I cannot tell you tomorrow is going to rain to do it any operations, because they have to prepare for the farming operations. So they need time scales of 10 to 15 days. So when break is occurring, we should be able to tell the farmer whether active spell is going to come, when it is going to come. And when it comes active spell, you should tell how many days it will persist and how many next time when the break spell is going to occur. So that is a beautiful research area where we are trying to do. We are doing it. There's a lot of success is happening, and still there are a lot of gray areas. This is a monsoon rainfall as a internal variation from this is IITM data, 1875 to almost 2023. And you can see that the black line shows the beautiful 31-year running average, and which clearly shows there are phases in which you have monsoon rainfall was less, and there are phases in which monsoon rainfall was more, then again less, and in phase. You can see all red lines, bars are drought years. Nobody speaking? You have some problem?
No, sir.
Shall I continue?
Yeah, please.
Yes, sir, please continue.
Yeah, so the red lines are all the drought years, and all these blue and green lines are excess years. And you can see that there are specific epochs, we call epochs, in which we have more frequent droughts. For example, in the 1901 to 1930, then 61 to 1990, then for afterwards, then we 2001 onwards there are a lot of droughts. But now you can see the last black line is showing this going up. So we are going, fortunately, this is good news, hopefully. Again, I put a word hopefully. We are going into a positive phase of monsoon rainfall. So last 4 years, we had good monsoon. we should expect good monsoons to come in near future. So that does not mean we will not get a drought, but the frequency of such droughts in that epoch, positive epoch, will be much less. And how monsoon is important, there's a beautiful paper by Godgill and Godgill, Indian GDP, because it affects the agriculture, even though 15% of Indian GDP comes only for agriculture. Earlier it used to be 50%, now it is only 15 to 16%. And still agriculture is a very important aspect, even though it contributes only 15, because many people are involved in agriculture practices. Farmer is a very big number. So it also has an important role in terms of, because if you farmer get more money, he will go and buy more things for his house. He'll buy a new TV, he'll buy a new car, he'll buy a new scooter. So it's also connected to the service sector and industries and so on. So monsoon rainfall is very important. But you can see the beautiful pattern of monsoon rainfall and GDP. It's not a linear curve, it's a non-linear curve. And the positive side, monsoon rainfall doesn't really pick up the good GDP. It doesn't really boost. Whereas a small deficiency or a big drought really will pull down the Indian GDP appreciably. Still, you can expect, of course, India is now very resilient in terms of economic practices, economic policies. Even a big drought isn't. Last summer 2015 was a drought, 19 was a drought. We never felt that, a common person never felt that it was a drought. Even 2002 was a big drought, but nobody understood that it was a drought. And because our government is our economic policies are very resilient to this kind of changes, but still within the government system it affects them, because they have to really make policies accordingly, changes the policies accordingly. So even now we can pull down by GDP by about 2%. It's a very big number. And how the monsoon variability is connected? It's connected with both Pacific Ocean in terms of La Nina, El Nino, INQUA phenomena, and also the equatorial Indian Ocean, so-called Indian Ocean dipole. There are two big phenomena which is really affecting monsoon variability in intra-annual time scale, year-to-year time scale. And there is another new factor is coming from Atlantic Ocean. People say that Atlantic Ocean also will play an important role. So the so-called El Nino in the Pacific, now they talk about El Nino in Atlantic Ocean, but it's not as efficient or as an efficient mechanism of internal variability. And as I told the black line, you can see there's a phases. So the large-scale multi-decadal variability is there, and which is very clearly shown in this paper, Rajesh by Goswami. You take the longest time series, which is from 1820 or so, and 2023. Still, it is a short time to understand the large multi-decadal variability, but then you can use very sophisticated statistical methods called empirical mode decomposition, and from that you can decompose the time series into different components. And so the IMF5, this one, the K, which has a time scale of 65 to 40, periodicity of 65 years. So this is the major multi-decadal variability component, and which is also related to the Atlantic, so-called Atlantic AMO, Atlantic multi-decadal oscillation. And so now understanding of multi-decadal variability is very important, and also the decadal variability next 10 years, 20 years, 30 years time scale. So it is this data are available even in this observation, this understanding of decadal variability is available even in paleoclimate. In the right hand side, there's a beautiful paper in a published scientific report which shows that even in proxy data, this particular variability was clearly seen. And these are the four regions where the forcing is coming. One is from Indian Ocean, one is North Pacific Ocean, one is the equatorial Pacific Ocean, one is. So there are four major. One is AMO, which is related to Atlantic Ocean. Then it's a PDO, so-called Pacific Decadal Oscillation. The El Nino multi-decadal oscillation, and Indian Ocean also play an important role. And in terms of area trend, you can see that trend monsoon is robust, and all India rainfall is still constant, but there's a lot of variation in terms of regional variation. And these are monsoon extremes. So in a particular season, particular day, it can rain very heavily. The rain which occurred this year, for example, at many places, it rains very heavily. As I told that we have noticed the changes in the rainfall characteristics in terms of heavy precipitation is increasing. This is the region where all red bars are there. This all shows the rainfall is heavy rainfall precipitation is increasing. 150 millimeter or more is increasing everywhere. That can lead to flash floods, large-scale river-based flooding. This is the bottom one you can see that 150 millimeter rainfall, the number of heavy rainfall over central India is increasing with respect to time. So monsoon in future, so I will spend another 10 minutes to conclude. So question is, so far we know how was our past climate monsoon, how was our present climate monsoon, and now question is how we know what monsoon will be, especially in terms of global warming. So what we do is we use S-system models to calculate, to estimate how much, to simulate what will happen in the next 30 years, 50 years, 100 years. And this is the so-called S-system, the climate system, which has many components, a very complicated system, nonlinear systems. And we need to model all these components in a coupled models, so-called S-system models. And we know that there is, why not go in theory of why the climate change is happening. I am very sure that you all will know, but there's a balance between the solar radiation is coming and S radiation going out. And if there is any imbalance because of any activity within the system, you can have an imbalance in the atmosphere, the energy balance, and it can make changes in the temperature. So what we are doing now is because of our own human activities, the concentration of greenhouse gases is increasing. That can cut down the lambda radiation which is going out to space. So there is imbalance between towards 1.5 watts per meter square. Also, the imbalance already is happening using satellite observations. We can see these changes. And this is how the carbon dioxide changes all greenhouse gases. It's a very famous paper. And you can see the last 2-3 points, you can see it just goes up, the vertical bar. So the concentration of carbon dioxide level, which we have seen in the recent few years, now it's almost 425 parts per ppm. It was not seen, it's unprecedented. It was not seen at least some 800,000 years ago. And this is a beautiful observation from Mauna Loa. So we should all thank this person, Dr. Keeling, who has put an observatory over Mauna Loa in Hawaii. And this is a beautiful observation, which is closely says, which now it shows about 425. And almost the aerosol is another component. So unlike greenhouse gases, aerosols are short-lived. Greenhouse carbon dioxide, methane and all can stay there in the atmosphere longer time scale, 30 years, 40 years, 50 year time scale, but not aerosol. Aerosol are short-lived. It's only maybe 1 week or 10 days time scales. But it has a cooling, mostly aerosols having a cooling effect when compared to the warming effect of carbon dioxide or methane. And when you talk about climate change, is a typical, if you know the statistics, you assume that everything is our climate system, monsoon system is a kind of a Gaussian curve or normal distribution. The mean can change. So if you change the mean, what is happening in the top left hand side top, you can see the extremes are also changing. So you can expect a change in the mean as well as the extremes, you should expect that to change. Assume that mean is same, but the variability changes. Again, the bottom middle one, you can see that the extremes are changing. And if both are occurring together, the mean also changing and variability also changing again. So the ultimate thing in climate change is not only the mean is variability changing, the extremes are also changing. So mean can change, the variability can change, and also it can change extremely. So this is a very important aspect which we need to understand. This is the beautiful temperature curve. You can see that last 30-40 years temperature has gone up, and 2023 was the warmest year ever recorded. And we solved this mathematical equation to predict the future climate, and this is the physics we use in the models. We use big computers of petaflop kind of time scale, the speed which we use for understanding the physics and model in the physics in the models. And this is how the models are good. So models are good. This is a simple answer I can give. But there are issues which I will talk about later. Left-hand side shows how the monsoon regions in terms of observations of rainfall. All green area shows the monsoon region. You can see that there's an African monsoon, Asian monsoon, South Asia, as well as East Asian monsoon. There's also the right-hand side shows how the models reproduce it. You can see there's a lot of good resemblance of models how reproducing the observations. The models are really able to predict, simulate may not be as simple. For example, African monsoon, you see the green color is on the model is much smaller than the green color. The intensity of the green color is very small. So that means the intensity is not able to provide, but the geographical distribution, spatial distribution, etc. The models are pretty good. So models have improved a lot, and models we can believe that we should believe. Not only we should believe these models. And then we assume them 4 or 5 different scenarios of greenhouse changes, then we can estimate how the future climate will. So before I go into the research, I would like to highlight this book. When I was secretary, we published the first National Climate Change Assessment Report. It was published by ATM, Dr. Krishnan and group. We should thank that group for doing this excellent work. But I should also congratulate me for putting this book as a free book in website. We gave money to Springer saying that we'll give you money, you please publish it and put it in online. We don't want money from this publishing of this book. And you can see how many downloads are there for, and now it is 520, it's old slide. 500K downloads and 524 citations, too good. So this is the way our publication should be. It should be freely available and online that people can make use of. So it's a very important contribution from Ministry of Earth Sciences, this climate change assessment report. First time we are doing it. This is the monsoon rainfall, how it varies, it will vary in future, how and different scenario, you can expect monsoon rainfall is going to increase. That's a good news. So monsoon is going to be robust and we'll have good monsoon. Because temperatures are going to increase, the more temperatures it can hold more water vapor and it can ultimately increase the precipitation. And of course, monsoon is not very simple explanation we cannot give in terms of this, but it is the basic driving force. And also the wind speed can go up and it can cause dynamical influence also it can. And how this is left-hand side is the beautiful paper. It shows that with every increase in temperature in Kelvin, there's an increase in monsoon precipitation. It's a linear curve. And if 1 degree warming, this much percentage, 2 degree warming can be little more. And right-hand side, the third one, very clearly shows that not only rainfall is increasing, but also the variability is going to increase. With every temperature change in the future, the variability is also, in terms of standard deviation, also is going to change. So there is a lot of disputes, and you can see that the scatter plot is not very good. But there is a beautiful meaning from this scatter plot is that when temperature increases, not only the mean rainfall is going to increase, but the variability also is going to increase. More variability is more to increase means more problems for prediction. So in terms of forecasting, the variability is more means more problems for prediction. And this is how the mean rainfall for 1 day rainfall is going to change with the different warming, 1.5 degree warming, 2 degree warming, 4 degree warming. So every warming, even 2 degree warming, there's in our Indian region, there's a percentage change is very high, 2 to 3% of expectation we should expect in annual maximum daily precipitation changes. And if you really plot this temperature, global warming, how much warming is going to happen now already the global warming is almost 1.1 degrees Celsius now, so it can go up to 1.5. We are trying to restrict it to 1.5, but it can go up to even 2. So 1.5 is highly ambitious plan, as I am very sure it's not going to happen, but at least 2 we should restrict. I'll spend another 2-3 minutes I'll spend another 2-3 minutes and I'll stop this. So global warming at 1.5 degree, you can expect about increase in event intensities. About 10-year event can be around 10%, and 50-year event can be about 12% change. And if it goes to 2 degree warming, then 10-year event can change about close to 14%, and 20 and 50-year event can change into 15% increase we can expect. This is very, very alarming. Very, very alarming. A 50-year event, 15% increase in 2 degree warming is very, very alarming. Already whatever we are experiencing, we are not able to control, we are not able to predict them properly. Some events, not all, some events we are not able to predict. Many people are, the reason why not is landslide was a good example. We could not do anything. Many people died. So, and this is going to, and it is all caused by heavy precipitation there. And this is the onset and retreat and duration. So what is models are saying Indian monsoon, the withdrawal is going to happen much later now in the future climate. So the monsoon duration will be much more. I mean, monsoon once it comes, it will stay back with us for a longer time. You may experience, we may feel that good, monsoon is with us for a longer period, but it will also cause a lot of problems for us. It will give you more rains, it will give you more intense precipitation, more floods, more landslides. So, but that's going to happen. And this is the rainfall intensity, intense precipitation, P20 or RX 1 day or 95%, all are showing about Indian monsoon region. with the temperature warming, the intensity of precipitation is going to change. And also there are concepts called flash droughts. People like Vimal Mishra and IIT Gandhinagar is talking about flash droughts. Like flash droughts also flash floods. Flash droughts also can happen. Basically changes in the soil moisture, and that is going to change in the future. And increasing risk of droughts. As I told that monsoon, with the global warming, you should expect monsoon rainfall to increase, but also monsoon variability is to increase. So both the sides, you can expect more and more heavy precipitation, floods, and also you should expect more and more droughts. So both the sides, you should expect more events, and this is a beautiful plot which shows that most of the rainfall which is going to happen now will be runoff. So not only the mean rainfall, the rainfall amount is going to happen, but runoff also is going to happen much more. Because I told that the characteristic of precipitation of monsoon rainfall is much such that it rains in few hours, it rains almost 50% of rainfall. So where the water will go, it will simply run off. So runoff will be much more in the future climate. So you should expect a lot of droughts. And also now talk about compound extremes. Not only one extreme event, but two extreme events can happen together. One is for some hot and dry summer, and that kind of things can happen. That also going to increase more. And I think this is the last slide. The Kerala 2018 Kerala floods. You must be all. There's one film also came, and we all know that dam was not properly managed, and there were a lot of casualties. Almost 2,000 people died, and a lot of damage. Ecosystem was completely damaged when they opened the dams. And so not only the water came out, everything came out from that, sediments, everything came out, because the dam was not open for many years. When it opened, everything came out, and it really destroyed the whole ecosystem. People died. And this is one study by Andan Aldi, so they are from UK, Reading University. So they told that the same synoptic system, if it comes in the future climate, the rainfall amount will be 36% heavier than the rain which occurred in 2018. Same synoptic setting and dynamical setting. The future climate, with the warming happening, the rainfall will be 36% heavy. It's very, very important message which is coming. And also, I did not put it here. The paper very clearly they told the present dams available in Kerala will not be sufficient to withhold the water which is coming from this heavy precipitation. So they need better, larger dams. That's the message. With that, I will stop. So monsoon is our bread and butter. We understand monsoon with the data thanks to a lot of observations, paleoclimate studies, in terms of observations, paleo proxies, and also paleoclimate modeling. People are doing it, and current observation from instruments and the current models using both climate models as well as future climate model, IPCC models. We understood the monsoon very well. Still, there are a lot of openings are there. There are a lot of gray areas are there in monsoon understanding. Every monsoon is. I have been chasing monsoon from 1994 when I joined the long range forecasting divisions. Almost 30 years now. Every monsoon for me is unique. You cannot say that this monsoon is similar to the monsoon on that year. You cannot say it. Every monsoon is unique. It comes with the unique features. So once you try to understand the problems of one monsoon, by the time next monsoon will come. So we are going accumulating the questions and answers. So it's a beautiful research problem. Monsoon is a beautiful research problem. It is close to my heart. I've done a lot of work. But still, if you ask me how good your knowledge of monsoon, I will say I know very little about monsoon. Very frank opinion, I know very little about monsoons. With this, I will stop here. Thank you.